So, who are we? So, we're Puppeteers. It's a company founded a few years ago by Petri, Lammi, and me, Samuli Seppänen. And we have done work before, like for years and years, like since 2006. But our company is pretty new, so only a few years old. And we mostly work on the DevOps field, also in identity management and identity and access management with Keycloak. So configuration management with tools like Puppet and Terraform and Ansible, plus identity management with Keycloak. That's like the short story. And we have our customers are like basically around the world, in Asia, in the United States, in Europe. So it really doesn't matter. We do all our work remotely, so it's really okay to have customers in any place in the world. We have like our experience basically is mostly on the Unix side, but we also do Windows. Originally, of course, like everybody else before configuration management and containers were invented, we did things manually, but like in 2008, 2009, since then we have been doing things in a DevOps style, using DevOps style workflows. Of course, it wasn't probably called DevOps at that point, but it's basically the same thing. So we were pretty early in the game. The company is based in Finland, in Turku, and we have a small office, but mostly we work remotely because it doesn't matter where we work from. I guess that's enough for who are we or who we are, so we can move on. So, as mentioned, the traditional way, and this is still being done a lot. I mean, this is the standard basically. So when somebody starts doing something, or all the systems basically, like Linux systems, Windows systems, the assumption always is, even today, that you will configure them manually. So you can do it with graphical tools, which is the case with Windows most of the time, or with web applications, especially like SaaS services like Slack, Atlassian suite like Jira, Bitbucket, Confluence. You configure them manually, so you go to a web UI or some desktop UI and you click on things and add data and whatnot, and that's how you configure the things you want to configure. On Unix compatible systems like Linux, BSDs, Solaris and whatnot, the traditional way has been the command prompt. So you type commands and the commands make things happen, and you use a text editor to edit configuration files. And on Windows, you have had the option to use a command prompt for a long while. Initially, of course, the MS-DOS prompt or the DOS prompt, and later around Windows XP something, PowerShell was introduced, which is like an object-oriented command prompt. And they have extended, actually Microsoft extended PowerShell quite a bit, but still in most cases when you configure Windows systems, you do it manually. You can do it automatically with PowerShell, but the de facto standard is still building it with the graphical tools. And the problem here, or the challenge with this traditional way of either command prompts or graphical tools, is that when you make a change, you have to do it. When you have to make a change several times, you have to do it again and again, basically. And what this means is that when you have more than a few servers or desktops or whatever you're configuring, you will probably just skip everything you don't really have to do. Like for example, you don't want to configure firewalls correctly on all the servers. You don't want to do some base configurations that are complex on any of the servers, because it would be too much work essentially. you would have to do all of it again and again and again on all of the servers or desktops or whatever resources you're managing. So we can probably move on to the next slide. Okay, yeah, I didn't actually notice. Yeah, this is the next slide, just the same title. So yeah, the other problems with this approach of building with on the command prompt manually or with graphical tools is inconsistency. Even if you're just doing it by yourself, you're the only person doing it, you will still forget how you did thing A or something on like one server. You will forget it when you're configuring a second server like a few months later. And this becomes even more problematic when you have several people working on the same set of servers. So everybody has their own way of doing things. So everybody is basically like an artist. So they want to have their mark of their work on the servers or the desktops. So, or even in clouds like AWS and Azure, if you let people manage them manually, they will do the configurations in the way they see best or what they think is best. But that may not be consistent with what you would want as like a manager or as an ops team leader or something. And then you have two options. If you want to actually control this problem, you have to document a lot, like document policies on how to do things. And you have to document the things you have configured or and keep the documentation up to date. And if you do not, then basically nobody knows what has been done on the infrastructure side. So you don't have any visibility. You have to go in and look like what was done here. How does this look like? You're clicking on Windows UI or you're in the Linux command prompt trying to figure out what is running on this server, or you might be in AWS or Azure consoles trying to figure out what was done here. When you're debugging, for example, and it's really difficult to keep the documentation up to date. I mean, nobody wants to write documentation if they can avoid it. So, and this is also a problem when you have to make changes. If you do not understand what the current state of the resources you're trying to change are or is, then you will have to go and look. You go look, what does this server do? And once you know what it does, then you can actually make the changes. But basically, this is lack of visibility is one of the big problems here, and inconsistency. So we can move to the next one. Yeah, and also humans, like we're not really good at making like changes the same way and correct changes every time again and again. That's a good job for a computer, but not for a human. So you usually, when you do things manually, you forget something. You forget some details. Like a typical example is that when you configure a service running on Linux, for example, you forget to enable it on boot. Or you may just make some small mistake in the config file and you don't notice because you forgot to restart the service after you made the change. And then when you reboot the server, the service will not come up like a database, for example, or a web server. It doesn't come up because the configuration file is incorrect. So that kind of things are really easy to make if you do things manually. And this inconsistency and ease of making mistakes basically leads to lots of issues, like small issues, but issues. And when you have an issue, you of course have to fix it. First, you have to figure out what is wrong. You don't usually know what is wrong until you have had a good look. So you have to track down the problem and then you have to fix it. And then the cycle will repeat when the changes are made manually again. And eventually something breaks again because of some mistake. And then you go again, you debug and you fix. So that's a cycle you will not get rid of if you do things manually. Okay, then we can move on. So this is the start, basically. Version control is the start of infrastructure as code. So even though version control is not really needed per se, it's in practice a necessity when you do infrastructure as code. So version control like Git allows you to track the changes you make into the infrastructure. And that's important, especially when you have multiple people working on the same code base or the same infrastructure. Because if you don't know what the other people did, what changes they made, it's really difficult to follow or have any kind of quality control, for example. So Git or other version control allows you to do proper change management. And this level is like above the actual tools you would use for configuration management or infrastructure as code. So it's like the common thing that all of these systems share and like the basis. Okay, we can move on to the next one. So what are the advantages of building infrastructure with code? So the visibility, which we mentioned, or the lack of visibility, which we mentioned when you manage the systems manually. So we get visibility into the infrastructure, at least the desired state of the infrastructure. So you can just have a look at the code, assuming you have everything under like a codified, basically written in code. You can just have a look at the code and you can figure out how everything is configured. Of course, it could be that somebody has touched something manually and it's the code itself doesn't reflect reality. But in most cases, if you have a disciplined team, the code is a really good representation of reality. The code gives you uniform because you can, like, for example, you can have a base configuration set which you will apply to all the targets, like servers, or it could be AWS or Azure resources, or it could be containers or whatever. But you can just do the work once and you can reuse it over and over again. So this is something which allows you to scale. For example, you can set up backup jobs automatically. You can add monitoring automatically. You can install packages automatically or whatever you want. So this is a clear benefit with this approach. Also, you will make less errors simply because you will do the things once, then you will just replicate it. So as long as the first change is correct, all the other changes that come after will be correct as well. And this, there's also one benefit, the last bullet point here. So the problem when you have a manually managed infrastructure is that you usually, the time from making the mistake to actually realizing that the mistake has been made is usually pretty long. So you make a mistake, but it might manifest itself only when you reboot a server, for example, or something else triggers the problem. But with infrastructure as code, you will actually spot the problems immediately. So you make the code changes, you deploy them to Git, they get deployed to the targets like servers or AWS, and things will break immediately, basically. So it's much easier to figure out what was that broke, what made things break, basically. So that's a benefit as well. It makes debugging a lot easier when you make a mistake. Okay, next slide. Okay. So repeating changes. So this refers to things like backups and monitoring, which I mentioned, and anomalies. Well, I'm not sure actually what I meant by anomalies. This is actually translated from Finnish. So I guess it's just easier to figure out if something like some configuration is not in line with the policies you have made or what your team has. That's probably what I'm after here. And reverting change is also easy. So basically, because you're using a version control system, you can also, if you make a bad commit, all you need to do in case of Git, for example, all you need to do is git revert and the commit ID, and then you push and you deploy. So if you make a mistake, it's easy to revert it. So when you, for example, contrast this with something you do manually, you make a manual changes, you make a mistake in 5 places, you do some base configurations or something, you add something to backups or monitoring. If you mess up, you will have to do it again 5 times to revert the change. But with this, because you can repeat the same configurations easily, it's left to the computer to repeat them. So it's really easy to revert if you need. So you basically get less downtime or less time of systems that are partially configured or partially functional. Okay, next. There's a typo here, but anyways, so routine maintenance. You don't really do much routine maintenance when you do infrastructure as code. You just make the configurations once and that's it. Basically, you modify it over time, but you don't really have to do any maintenance per se. I mean, the maintenance is writing the code, making small changes occasionally and so forth. And inventory as well. This is basically about the visibility to the infrastructure. So you actually know what you have running, which is actually a problem in AWS and Azure, like public clouds or Google computing platform. Say a virtual machine might cost you $30, $50, or maybe even $100 every month. So you really would want to know what you have running, but most people don't probably. So the inventory you get by using something like Terraform in the context of AWS or Azure, it really helps you understand what you're paying for. And you can also get rid of the stuff you don't need if you have everything in Terraform, which is, we will get to Terraform later, but it's basically an infrastructure as code tool for, among other things, for managing public clouds and private clouds. And also, you can manage the life cycle of the system you're managing. So it could be a server, it could be a bare metal server, it could be a desktop with Windows or some AWS Lambda function or whatever, any cloud resource. So you basically, your life cycle in this context means that you will create the resource somehow using provisioning, PXE boot in case of bare metals, Kickstart installation, and then like some configuration management system. Or it could be just that you create some resource in AWS, and then you have it running, and eventually you don't need it anymore, you destroy it. So you can automate the whole life cycle of the things you're managing if you want. You don't have to, but you can. And then we can probably move on again. Yeah, so when to use infrastructure as code? Well, I mean, optimally you would always use it, but that's not a good answer, because sometimes it's really difficult to do things as code or write something into code. And also, when you're starting up, I believe we have a slide about this as well, but if you're starting up, you really don't want to do the always part. You want to do the low-hanging fruit, the ones that bring you most benefits, basically. Best cost, basically return on investment. But especially like repeating configurations, those are good start. So like if you have servers or desktops, you would start from the base configurations, like installation of packages you will need on all of them, settings of some system daemons or services, monitoring, that's a good use case, backups, everything you would have to repeat manually on all of the instances you're managing, or servers, desktops, or whatnot. And the same basically applies if you're managing like public clouds or some other API, something you can manage with an API, which means that you would be using Terraform probably. So whatever that repeats a lot, that you will want to automate first, because that gives you the best return on your investment. Okay, let's move on to the next one. Yeah, we covered this as I had a hunch that we have this slide. So I won't repeat any of this because I covered all of this. So let's just move on to the next one. So you have a couple of approaches to managing configurations with code. And one of them is based on so-called desired state. So basically, the traditional way, I will use like Unix command prompt as an example. So on a Unix command prompt, you will be running commands and modifying text files. So it's like imperative approach. So you order the computer, like the server, to do something. And by doing these things, you will basically make it behave as you would want. And the configuration management based on a desired state is different. So the actual steps on how to reach the desired state are not important for you as the administrator or the DevOps or whatever you want to call yourself. Instead, you define the state of the resources you're managing in code, and the actual configuration management system will ensure that the resources are in the state you have defined. So if there's a difference in the current state and the desired state, the system itself, the configuration management system, will actually converge the current state into the desired state, or at least try to do it. So you won't be running any commands or scripts. Instead, you will basically you will create a model of what you want, and the configuration management system will make the configuration comply with the model or the desired state. And then, well, I guess we have a second slide about what we would actually manage, but if not, I will explain it, but let's move on. Yeah, as I remembered. So all of these tools, and we will list these tools and discuss them briefly later on in this webinar. All these tools basically manage like atomic components or parts of the system configuration. So on servers, desktops, workstations, you would be managing things like files, packages, services. On Windows, you would be managing registry entries and so forth. You could manage firewall entries like IP tables, rules, or Windows firewall rules, or something like it. So it's like a single item or object you're managing. And on the cloud, and this actually is not just cloud, but in public clouds like AWS, Azure, you would be managing like instances, like virtual machines, routers, routing tables, domains, Lambda functions, and so forth, or also security groups and that kind of things. But they'll basically, each of these is more or less independent of everything else. So this is what you are managing with these configuration management systems. And we can move on to the next one. And within this, well, this is actually not even tied to the state-based configuration management approach, but you have two approaches of managing things. So you have the push model. So you could have, basically you push the desired state, for example, to a cloud or to a server. So you define the state, then you push it. So you take an active role. It's not automatic in the sense that you have to do something, you have to push. And this is the approach that Terraform and Ansible, for example, use. Then you have the pull model. So on the managed systems, you have something which you can call, usually you call it an agent. which will ensure that the desired state is always up to date, or always at least with some delay. And this is the approach that some systems like Puppet and Chef, they have taken this approach. And this is also, of course, this agent-based approach is mostly applicable to traditional servers, or like servers, workstations, virtual machines, and that kind of things, because you cannot really have an agent running on AWS or Azure or some other cloud. You have to push the changes you have through using an API, for example, with Terraform. But we can move on. Okay, so now to the actual tools. So Terraform, the usual use case is for managing cloud resources in different public clouds. But it's not really limited at all to clouds. So the limitation is more about having an API against which you can build a Terraform provider. So Terraform, while it can be used for cloud management, most of the clouds actually have a provider because it's sane for them. You can also manage things like network devices if they have an API, and most of the high-end or better network devices do have an API, and they usually do have a Terraform provider as well. So you can configure network devices as well. Terraform has also extended recently into managing applications. So it actually is going where the traditional configuration management systems like Puppet and Chef and Ansible have been. Like, you can potentially manage applications running on a server or in containers in Kubernetes or whatnot. You can manage them with Terraform if they have an API and have a Terraform provider. And the benefit with Terraform, besides it being the only tool really to be able to pull this off, like this multi-cloud, multi-device, and being able to manage all of this at once, is that you can actually integrate things together. So a typical example, which we also use, is to create instances like servers, virtual machines in one cloud, but use DNS in another cloud. For example, we use Hetzner for the instances, but we have the DNS entries for the instances we have actually in two places. We have them in FreeIPA, plus we have the public DNS records in Route 53, which is in AWS. So you can tie all of this together into one Terraform code base. So when you create an instance, like a virtual machine, you can also automatically add DNS entries for it so that people can find it more easily. So that's basically Terraform in a nutshell. And this is push model, I should add. So it just drives the APIs that the clouds have, basically, and the devices, network devices, and so forth, and the applications have. And I guess we can move on to the next one. So another tool we use and many other people use is Puppet, and this one is like a traditional, on quotes, configuration management system. It's really useful for managing physical, like bare metal instances or servers, as well as desktops, whether they're Windows or Linux or Mac OS X, and so forth. So basically classical stuff. This is not a container management solution or anything. So it basically manages the operating system and everything beneath it. It doesn't really manage cloud resources, even though that one is also possible, but it's not the best tool for the job. So you manage packages, files, services, and Windows. You have PowerShell DSC support, which is really good. I would actually claim that Puppet is the best way to manage PowerShell DSC, meaning managing Windows installations. Puppet can actually be pull model, meaning you have a server and you have the agents. But a few years ago or so, Puppet introduced a tool called Puppetbolt, which will allow you to orchestrate changes as well as manage configurations by pushing them using either SSH on Linux or Mac OS X or WinRM on Windows. So you can use the same code. You can use push model or pull model. So But that's probably enough for Puppet because this is just an introduction. And let's move on to the next one. Yeah. So then you have Ansible and Puppetbolt. They're pretty similar because they both are basically orchestration tools that can also do configuration management. So orchestration in this context, it means basically you have some set of steps. For example, you make a software release, you have some complex application which has a database, it has web application, it may have some support services and whatever, and you're making a release. And you would orchestrate this release using some orchestration tool. This is under the assumptions that you don't have anything like Kubernetes or something that would handle all of it. So, but basically you do a sequence of steps in a certain order on certain target nodes. So you might want to update the database first, for example, or you want actually first upgrade the application running on the web servers. Then you would update the database schema, and then you would finally restart the applications, or for example, web servers. So that's basically orchestration in a nutshell in this context. So the order is important. You cannot just do all at once. You have to do it in a certain order. And in this use case, you can use Ansible or Puppetbolt, or some other tools are available as well. And the model is just like with Terraform, it's a push model. So you don't have any agents that would actually somehow figure out the correct order. Instead, you define the correct order, and then you make the changes. And we can move on to the next slide. So Docker is, well, everybody knows Docker, it seems. So basically Docker is a containerization technology. Basically, there's lots of misconceptions about Docker, but it's a packaging format. So you package a set of resources, basically a file system snapshot. You package it and you add some metadata, and the result is that you can launch an application that has been converted into a Docker using a Docker file. You can launch it, and it is basically self-contained. So you can run it. You can have the initialization command. So you have like a web server Dockerized. You just copy it to somebody else, for example, using Docker Hub, and he or she can just launch it, and it will basically be identical. So it's basically a distribution, way to distribute software, but you get other benefits as well. This often people think of Docker as a lightweight virtual machine, and it kind of is, but it's also a bit misleading because it's not really a full virtual machine. It's basically like file system level isolation, which uses some of the fancy features in the Linux kernel, so that you have isolated, basically isolated runtime environments. And I mentioned that it's misleading to think of them, the Docker containers, as virtual machines. And the reason is that you cannot do everything you can in a virtual machine in a Docker container. So the capabilities of a container are actually limited by privileges. So your capabilities, they're called. So you cannot, for example, run OpenVPN or something that requires modifying network interfaces in Docker container without also granting the container like pretty large array of capabilities, which is not good for security. So usually it's better to think of the containers like you have an application that's containerized. You would actually build it from several containers. So you have a database container, you have a web application, web server container, and you basically just glue these together. They're separate, and you glue them together. You don't push everything into the one container, even though you can do it, but it's not the best practice. And because you have multiple of these, if you distribute your applications, you will also need an orchestration solution like Kubernetes, for example, which is the coolest of the cool nowadays. But like basically Docker, it's also infrastructure as code because you write the Docker file, which is a recipe on how you would build the container. I don't like the approach of building the containers because it's basically shell scripting with some syntactic sugar and some Docker specific commands basically, but essentially you're configuring the application, be it a web server or a database, you're configuring it with shell commands, which gets pretty ugly pretty easily. So it's in that sense, it's actually going backwards from the traditional configuration management. You can build Docker containers with Puppet, Ansible, or whatever, but it's not usually done, and there are caveats, and it's not really nice that way either. So, but they're here to stay, and they really do have benefits in many areas. So we cannot really ignore them, and nor should we. But let's move on to the next one. So, so this is about ensuring quality of your code changes, and with Docker, I believe most of this actually goes out of the window. Not everything. But more traditional configuration management, at least Puppet, Ansible is not as good with these as Puppet is. But you can actually do automated validation of your code, also linting, like making sure that the syntax is correct, making sure that you're following the best practices in writing your code. You can even have unit testing. In case of Puppet, that's RSpec or RSpec Puppet. So you can actually, when you make a code change in a Puppet module, you can actually have like thousands of tests launch immediately to make sure that you haven't introduced any regressions. And also acceptance testing using Beaker. This is somewhat related to Puppet, but I believe other platforms can use, they have their own tools, like Chef has its own tools, and Ansible, well, Ansible, I don't think it has any real test frameworks, I'm not sure. But anyways, you can run acceptance testing, which basically is an integration test in this context. So suppose you have a cluster, it could be a key clock cluster, it could be some other cluster. You can run the acceptance tests with Beaker to test that when you make a change in the Puppet module, the cluster will still be fully operational. And basically, the acceptance testing works by provisioning test systems, system under test, like a master server and a replica server, for example, and it will do a replication test. Make sure that the services, in this case, Keycloak is running, and it will add some data into the database using API commands or API calls. Then it will check that the other server, the slave, has the same changes. Then the slave server will get rid of the changes, and we will check if the deletion of the changes is present or has happened also on the master. So basically, you can do cluster testing. So whenever you make a change, you can run through this acceptance test automatically to make sure that you didn't break anything. And server spec, well, briefly, it's basically a way or a tool to test that a server is configured properly, everything is running as expected, file contents are correct and so forth, but no need to go into it in any detail. So let's just move on. Yeah, then other ways you can test. This is, I guess, well, you cannot really do this with Docker because the containers are replaced when you deploy them. But you can, in Puppet, Ansible, in the traditional configuration management, what you can do, you can make the changes. Then you can test the changes with no operation mode, which will show you what changes would be made, but no changes will actually be made. And this will actually help you spot problems early on without any risk, really. So no changes will be made, but it's like a simulation of the changes. Then you can move on to testing on a production node. Of course, no, not slides, but yeah, anyways. So you can test after you have done the no operation testing. You can do the test on single. Well, it doesn't have to be production actually. You should always have like a testing environment, but usually it's, especially in a mixed infrastructure with lots and lots of different types of servers, like dozens, it's really tedious to create proper testing environments. So you can take the shortcut in some cases and test on like in production, in operation. Then you can move on to actually doing the changes on a single production node that you know is going to be affected by your changes. And if all looks good, you can deploy the change to other ones as well, if you have, like, say, several web servers or something. And of course, once you have deployed, you should have the monitoring in place so that you can actually figure out if, even after all of this quality assurance, you have broken something. So you need to have monitoring in production, and preferably if you have a proper staging or testing environment, you should also monitor that one so that you don't actually have to break things in production. But anyways, I think we can move on. Okay, so how to ensure the quality before you go to production? So you can use different tools. You can use Vagrant, which is a tool we use quite heavily. So Vagrant is basically a wrapper around virtual machine backends, usually VirtualBox, but it supports other backends as well, like Hyper-V, libvirt, and so forth. So what Vagrant does, it allows you to create test environments or development environments automatically. So you define some base image, say Ubuntu 2004. You provision it with Vagrant, which basically just commands VirtualBox or some other virtualization backend to create a VM, after which it provisions the system, meaning it runs commands or runs Puppet code or does something to configure it the way you want. And Docker is actually not that different. And Docker is actually used nowadays a lot for software testing. Even in the Puppet world, you use Docker for running acceptance testing, for example. So basically, the approach is exactly the same. Vagrant is virtual machine based, Docker is container based. Otherwise, they're pretty much identical in this use case. So Docker is faster because you don't have to actually spin up a full VM. You just spin up a container, which is almost instantaneous. Then you can use dedicated test environments, which is especially useful with Terraform. So suppose you manage a cloud for a customer or somebody, even yourself, and you want to make sure that when you make changes with Terraform, you don't want to break anything. With Terraform, as well as with Puppet and Ansible and whatever system, it's trivial to create a separate test environment. You just basically encapsulate your environment, whether it be production, staging, testing, or whatever. You encapsulate it into a module and you pass some parameters to the module to define how what the environment will look exactly. So you can have, like, for example, production environment is the same as the staging environment, except that certain parameters like AWS region or something change. And you can basically create the same environment multiple times, and they will be really close to each other, just some minor changes, some minor parameter changes. Then you can actually use the testing or staging environment before you go to production. And probably last but not least, is the forced code review. So this is just like peer review. So this should be a policy, in my opinion, in any place that has multiple people working on the same code base, especially if there are like junior guys who haven't done much yet, who don't know the tools well. It's really important to review the code, because then you see if the code is actually good. Does it have any side effects? when somebody has lots of experience in certain tools like Puppet, Terraform, and lots of experience in the infrastructure as well, it's quite easy to spot mistakes somebody else is about to make. So the code review allows you to fix many things that cannot be fixed by, well, automated testing like acceptance testing can catch same kind of problems, but having a forced code review is always a good idea. So if there's a problem, you just ask the author to fix it, and you repeat until everything looks good, all the tests pass, and then you can move to production in steps, like testing first and so forth, staging next. Okay, let's move on. Oh, it ended, really? Okay, I was just about to get started. But yeah, okay. So this was a really brief introduction, which seemed to have taken like 50 minutes. We had 1 hour. But any questions?